So let's start. It says, Introduction to Forces. A force, I could give you a fancy schmancy physics definition. A force really is a push or a pull. I gotta be honest, there are some forces, Aaron, that technically aren't obviously a push or a pull. We'll get into those bizarre ones next year. But for now, what's a force? That. Or that. A push or a pull. The object in question doesn't necessarily have to move. I'm applying a force to the sink. It didn't move. Is force a vector or a scalar? Does direction matter for a force? I wonder. Greg is nodding his head. He thinks direction matters. Greg, my friend, could you come stand right here? And Nick, now that you're done saying bad words, could you come stand right here? And I need a volunteer to stand in between you two. Oh, come on up. Let's stand right here, please. And come on, can you face Ron? Both hands there? Roy, sorry. Both hands there, both hands there. Push. 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 Stop. Can you go behind Greg for me? Stay here. Put your hands on Greg's shoulders. Push. Push. Okay. You saw a difference, yes? It was the same two forces they applied. Did the direction make a difference? You can sit down. So, scalar or vector? Did the direction make a difference? Scalar or vector? Clearly a vector. The symbol for force, capital letter F, although we should add a vector symbol above it. And force is measured in newtons. Named after a scientist whose last name was Sir Isaac Newton. You could make an argument that the best mathematician / scientist in history, the most influential, probably Sir Isaac Newton. If we're making a short list of scientists, we would say Einstein, Newton, and Archimedes. We give Archimedes credit because he was way ahead of his time, and he was way ahead of his time using Roman numerals to do all of his arithmetic, which is really impressive. Symbol for newtons, capital N. Example 1 says, find the blank force. What's the word in front of the word force? Begins with the letter N. What did I write? Net. The net force is the sum of all of the total forces, the net force. What's the net force, do you think, in object A? 7 newtons. Direction. Yep. Compare that with situation B, where you still have a 5 Newton force and a 2 Newton force, but I'm going to suggest the net force is not 7. What do you think it is? 3. Direction? What do you think the net force is in part C? 0 newtons. That situation there, 0 newtons, is going to be very, very important. What I'm going to tell you in a little bit is, if you have 0 newtons of force, the object won't accelerate. When Kayvon was in the middle and they were both pushing in opposite directions, was Kayvon accelerating? I can tell you the net force was 0. When they both went in the same direction, was Kayvon accelerating? I can tell you the net force wasn't 0. There was an unbalanced net force. I don't know how big it, but I can tell you it was there. D. What's weird about D? Those of you that take Physics 12 next year, you're going to find the first half of the course is Physics 11 done over again, but in 2 dimensions, and way faster. Oh, and if you take first-year physics in university, and a few of you will, you're going to find first-year university physics, the first 80% of it is Physics 12 done over again, but in 3 dimensions, because we live in a 3-dimensional world. With 3 dimensions, though, you really need calculus by that time, which is why they kind of save the 3D stuff. But 2 dimensions you can do with lots and lots of trig. And by the time you get to grade 12, you're pretty good at getting tricky with it. Shut up.
So what would that
The magnitude would be the hypotenuse of the triangle using Pythagoras, and then you would find angle theta. That's opposite, that's adjacent. The angle would be the inverse tangent of 3 over 6. So whatever 6 squared plus 3 squared square root, that's the magnitude. You add, what you're doing is you're adding vectors, and you're going to learn, we will do some of this later on this year. You'll learn that we add vectors by drawing them tip to tail and doing triangles. Newton's laws of motion. I got to go on a little rant about Sir Isaac Newton. One of my, I can't call him one of my heroes, but one of the people that has impressed me the most when I've read about him. When Sir Isaac Newton was around 20 years old, he was in university in London, not an exceptional student. He was a meh student, C plus B. Didn't have that kind of grades back then, but that's the records that we read. When he was in London, when he was about 20, the Black Plague, the Black Death, the plague came to London. And back then, if you were wealthy, and if you were going to university, Stefan, you were wealthy back then. If you were wealthy, if you could afford it, and the plague came to the city, you left. You let all the peasants die off. Their bodies would all go unburied, rot, spread the disease more, kill off more. Eventually, after a couple of years, anybody who was susceptible to the plague would have died off. Okay, and then you'd come back. And so he left. He went to a farm. He was a gentleman farmer. Not a farmer the way you and I think, like, using a hoe and a rake and digging. A gentleman farmer is the one who wanders the fields like this, with his hands behind his back, dressed fairly nicely, telling his peasant farmers what to do. He wandered the fields. He basically did nothing for about 2.5, 3 years. And you can make an argument, Brad, that during that 2.5, 3 years, no other human being in history has thought as much, has redefined as much, has discovered as much up here. In that 2.5 years, he invented the calculus. We put a "the" in front of it to make it sound really, really impressive. He invented a whole new branch of mathematics that completely revolutionized, made millions of previously unsolvable problems that you could only solve by guessing and checking and guessing and checking and guessing and checking, instantly, easily solvable. He came up with the law of gravitation. He, during this 2-year time, realized that white light is not white. It's made up of all the colors of the rainbow, and explained how rainbows work. Not much older than you guys. And one of the things that he did is he redefined how moving objects move. He gave them 3 laws. We call them Newton's 3 laws of motion. And we got to give him full credit for this, because in doing so, he basically flipped the bird to 2,500 years of science. Let me pause the video here, and I'll tell you what the Greeks and everyone after that believed. So Newton's first law is called the law of inertia. He phrased it as follows: objects at rest tend to remain at rest. Objects in motion tend to remain at motion. That's a confusing way to phrase it. Here's how I phrase it. If an object is accelerating, there has to be an unbalanced force. And it works backwards. If an object is not accelerating, which means you're either going at a constant speed or speed 0, then the net force is 0. That's Newton's first law. So look at Nick right now. Is there a force acting on Nick right now? What? Gravity. Are you sinking into the earth like quicksand? Are you flying into the air like Superman? Are you accelerating? Then there has to be net force of 0, which means gravity's pulling you down. There has to be another force exactly the same size pushing up in the opposite direction, the ground. Oh, and if the ground suddenly vanished like a trap door, now you no longer have now you no longer have a balanced force. You're going to accelerate. Now you're unbalanced. Okay. When I roll this ball, it wants to keep going in a straight line at a constant speed. A force, not a very big one because it takes a while, a force is acting in the opposite direction, slowing it down. Friction and air resistance, mostly air resistance. If it's not rolling, friction. Ready? Watch your hands. I applied a force, it moved for a little bit, it slid for about another 1/10 of a second and came to a stop. Friction kicked in, unbalanced force in the opposite direction. Your bodies are built-in accelerometers. Your bodies can feel acceleration, but the problem, Race, is we feel it backwards. We feel it backwards. For example, when you're in a car and someone hits the brakes, which way does it feel like your body wants to move? but which way is the car clearly accelerating? Yeah, we've learned that, yes? How many have been on the elevator before? You've been on the elevator? When it launches you up, which way does your stomach feel like it's being forced down? Which way are you clearly accelerating? Up. So by the way, a rule of thumb that I have, if I'm ever on a ride or in a situation and the nerdy part of me says, I wonder which way the force is, which way do I feel like I'm being pushed? Opposite direction. So, how many of you have ever been in a car that makes a left turn? If you're in the passenger seat, you feel like you're getting pushed against the door? It's not right. You're actually getting accelerating inwards. What's really happening is this. If you're driving in the car, your body has inertia. It wants to keep going in a straight line at a steady speed. When the car moves underneath you, your body wants to keep going in a straight line at a constant speed. And what happens as the car moves underneath you, the door or the wall panel has to push against you, has to exert an unbalanced force to get you to accelerate that way. You don't think of that. You feel like you're getting pushed against the door. You're not. The door is pushing against you. Okay? So imagine you're a passenger in a car and the driver makes a sudden left turn. What sensation do you feel? From your own experience, you feel like you're being pushed to the right. I'm telling you, you're accelerating in the opposite direction that you feel. Your body is a built-in backwards accelerometer. Contrary to what your common sense tells you, you're not being pushed to the right at all. The driver steers the car to the left. Your body wants to carry on a straight line, but the door of the car is moving left with the rest of the car. You feel as though you're pushed against the door, but actually your body is trying to continue in its original path while the car is turning left. Turn the page. As a general rule, an object wants to keep going with whatever speed and direction it presently has. The object does not want to change its speed or direction. We have a fancy word for change in speed or direction. It begins with the letter A and rhymes with acceleration, which is why we always start out with acceleration, VI, VF, all that, and we're going to be using a lot of that stuff as well. And hopefully you can recognize acceleration now when you see it. It can be a change in speed, or it can be a change in direction, because you might be going around the corner at a constant speed, but you're definitely accelerating because there's definitely a force acting on it. The more massive you are, the more mass an object has, the more it will resist a force. The more it will resist change. The more it will resist an acceleration. And we give this ability to resist their change in their state of motion a name. We call it inertia. Inertia. It's related to mass, and I'm going to be honest, most of the time this year, Jamie, I'm going to use, sorry, Jamie's over there, not sitting there anymore. Jamie, I'm going to use inertia and mass interchangeably, even though I shouldn't. For this year, it will suffice. Keeping in mind that really I'm wrong. Okay? More mass, more inertia. Every object in the universe that has mass has this property of inertia. So what has more inertia, a bicycle or a logging truck? What does that mean then? Because it has so much more inertia, that logging truck is much more difficult to get started from a stop. That's why big semi-trucks take so long at a red light to get going. It's nothing to do with the driver. Inertia. More difficult to bring to a stop. That's why semi-trucks and things take longer to stop. Freight trains take a really long time to stop. And more difficult to turn at a corner. That's why trucks got to gear down, slow down. How do we measure inertia? Mass. Kilograms. And again, I'm technically, you know what, we'll just say I'm right. I'm technically wrong. But right now, the best measure we have for inertia is the amount of mass an object has, and we measure the amount of mass in kilograms. So, how does Newton's first law help explain how seatbelts save lives? What do you guys call it when you want to sit in the front seat passenger side? You've given it a name, your generation. Huh? Shotgun. Do you know where that name came from? It came from the pre-seatbelt days. Back when cars had seatbelts, but they weren't enforced. We used to joke back in the 50s and 60s, the joke was if you were sitting in the shotgun seat, you were called that because if I had a head-on collision, you were the first one out to inspect the damage through the windshield, right? You'd go through the windshield and you'd see where the bumper had been damaged. You were in the shotgun. Why didn't they call the driver the shotgun? Because there's an obstacle in the driver's way. What? Steering wheel. He would smash himself and kill himself on the steering wheel. Okay. Why? Both of them want to keep going in a straight line at a steady speed. So how can we fix that? Seatbelts. The early ones were terribly made, so the ones back in the 60s and 70s, they had the lap belt, but they brought you to a stop instantly, which meant you break your ribs, but you're alive. I don't know, the newer ones, you'll notice they have a tiny bit of flex, like about a half a second's worth of flex. What you'll get is the seatbelt bruise and rash, but you probably won't get the broken ribs and you'll be alive. Simple invention, cheap invention. If you're bored sometime, look into the history of the seatbelt and how tough it was for people, for the guy who invented it, to get car manufacturers to adopt it. Technology hasn't changed all that much. Oh, saved. You know what? I'll bet you it has saved millions of lives at this stage. How many of you have been in a car accident? Okay. I've been in a few. I had 1 year where I had 3. Oh, how does seatbelt explain how how does Newton's first law explain how seatbelts save lives? Person wants to keep going in a straight line at a constant speed. So, seatbelt applies capital F force in opposite direction. So I wrote down here car accident story. Good demo. I'll show you a video in a second. So the demo, Kayvon stayed dry. Woohoo! The old magician pulling the cloth out from underneath the dishes. When I was about 26, I was doing my student teaching and I got rear-ended by a semi-truck. Yeah, it wasn't a good one. I came out okay. We were on the freeway just before the SFU exit, just before the Burnett exit, so one exit before SFU, and it was stop and go traffic. And the person in front of me hit the brakes, I hit the brakes, and the semi-truck behind me, he had just looked down to grab a cup of coffee, and by the time he looked up, he hit me. And I clearly, it's because when you're in a car accident, you know, the whole time slowing down, I mean, you really, your brain goes into super observation mode. I had an ashtray, which tells you how old my car was. There was an ashtray, and I had all my spare change in it. Probably had about that much change by that time. Had some good inertia, some good mass. When I got rear-ended, my ashtray went shooting back over my shoulder and hit the back seat. No, that's what I saw. What really happened when I got rear-ended, my car got thrown forward with me in it, wearing my seatbelt, but this change tray had enough inertia that it wanted to stay where it was. Just like when I yanked out the table, the paper towel, that water tray wanted to stay where it was. My car moved forward, and the change tray dropped down. But relative to me, it appeared as though it went shooting back over my shoulder, right? Because I moved forward instead. I got thrown into the car in front of me. My front crumple zone, my engine got all, well, my engine basically became my front seat. The back trunk became the trunk became my back seat. I was fine. I banged my knee. My mom came to pick me up. She started breaking down. I had to sit her down for a while. Mom, I didn't die. I'm fine. I'm my little boy. I'm fine. Okay. In terms of physics, it was a great car accident. And I guess, you know what? Statistically, most people will have one car accident. It was a good one in that I banged a knee. I had a tiny bit of whiplash. I was sore for a couple of days. I remember that. Took a couple of Tylenol. Newton's second law is the equation, the main equation for this whole unit, that which everything else will derive from. Newton's second law tells us how to calculate force. It's F equals ma. It's on your formula sheet, but you'll memorize this one because you get tired of looking it up, and it's pretty easy to remember. Which are the two vector components? Force and acceleration, which means whatever direction you're accelerating in, Janaya, that's which direction the net unbalanced force must be. Doesn't mean there's not forces in a different direction. It just means when you add them all up, the unbalanced net force is in the same direction as the acceleration. Oh, that means something else. Jacob, do you remember the units for force, what we said at the very beginning? What's force measured in? Named after a famous scientist who went on a big rant about it. By the way, hopefully you've clued in. It's worth memorizing what units go with what, because it sure makes the plug and chug easier when you're listing your DFIC. Yeah, you can figure out right away what it's. So add newtons to your list. But since newtons is force and force is mass times acceleration, I think that means that a newton is a kilogram meter per second squared. It's a mass acceleration, is it not? And it was called that for a long time. Till about 100 years ago, Jamie, they said, hey, let's give this unit a name, a newton. Do they still change units and give units names? There is talk right now, they're talking about renaming a certain unit an Einstein, and I'll tell you which one that is when we get there. They haven't yet. They're talking about naming one after him. Example 3. Malcolm has a mass of 65 kilograms. What's the magnitude of the gravitational force acting on him? What am I asking you to find in this question, Greg? Force, F equals ma. Greg, my friend, is there a mass in this question? What? Now, the second thing is the acceleration. I didn't tell it to you. I didn't need to. Hey, what is the acceleration due to gravity? Now, and oh, good, you ditched the negative. Last unit, because we were always interested in up, down, and direction, we include the negative. This unit, later on, we'll have some stuff moving up and some stuff moving down in the same question. So we'll temporarily ditch the negative and we'll decide which way is positive. For now, let's just put in the 9.8. And what is 65 times 9.8? How many newtons of force is gravity exerting on Malcolm? 637? Newtons. All of you right now have between 500 and 1,000 newtons of force acting on you, and you're used to it. It's gravity. In fact, you're so used to it that when they muck around with it, like on a good amusement park ride, you'll pay money for it and you'll get scared. In a healthy fear, the kind of scare we like, where things are still in control, but it's a rush. The space shuttle has a mass of 2.03 times 10 to the 6 kilograms. It does, I looked it up. If each engine is capable of exerting a force of 12.5 mn, what does the capital M stand for? Oh, meganewtons. And I looked that up. That is what they're capable of exerting. What's the maximum acceleration of the space shuttle? Okay. Joel, what's this question asking me to find? Let's write down A equals. Now, last unit, when you wrote down A equals, you'd be hunting around for a V final or a D or a T. Okay, we're broadening our skills now. What have they told me? As I scan this, I see a 2.03 times 10 to the 6th. Amanda, what's that? How do you know? Kilograms. Okay. And as soon as I see that, I start thinking, I got an M, I got an A. I'm thinking force. Now, did I just tell you how to figure out the difference between last unit and this unit? No. Yeah. What's the force? Well, it says there's two engines. Each force can exert 12.5 mega. What is that on your? Someone has their formula sheet. What's the? You got it in front of you, Abe? What's capital M? 10 to the what? Help me out. What's mega? 10 to the what? 6? Okay. I would start out by saying I'm looking for an equation that has A, M, and F in it. I think it's this one. Okay, how would I get the A by itself? Yeah, thankfully, this is a nice, fairly clean equation. By the way, this was actually the equation that Newton was interested in. He was less interested in force. He was much more interested in acceleration. Come on, pen. Why are you not working right there? Okay. Now you'll write. Go figure. The force is going to be 2 times 12.5 times 10 to the 6th. And 2.03 times 10 to the 6th. I can use my scientific notation, but I'm kind of curious, what do the space shuttle astronauts experience? What kind of an acceleration? 2 times 12.5 scientific notation button 6 divided by 2.03 scientific notation button 6. You get 12.3? Someone double check me. Divided by, not minus, divided by. Brad, you get 12.3? Perfect. Units. Acceleration. Units. Meters per second squared. Yes? I'm just curious, how many G's is that? Can someone divide that by 9.8? How many G's is that? 1.25. That's tame. On the elevator, you get about 2.5 to 3. Space shuttle actually isn't that exciting a ride in terms of the physical forces. It's exciting a ride in terms of where you're going. Then I wrote here, why does the maximum acceleration change as the engines burn? Because it does. Cole got straight to it. Since the acceleration is the force divided by mass, if the acceleration is changing, either the force is changing or the mass is changing. The force isn't the engines put out a constant thrust. But why is it getting lighter?
It's using fuel on that.
Using fuel.
And after
If, in fact, as it turns out, it's so tough to get stuff in outer space. Once you've used up the fuel, the engine is useless. That's why the Apollo rockets were 3-stage rockets. Once we've used up that fuel and that engine, get rid of the mass. Why? Because F equals ma. Lower mass, same force, means more acceleration. Darn right. In fact, how does Newton's second law help explain why a sprinter might want to wear lightweight shoes? It's not to do with gravity. What's a sprinter interested in? Acceleration. Did we just on the previous page write acceleration in terms of force? Yeah, let's write it again. Nope. And then, Nick, let's talk about Usain Bolt. Let's assume Usain Bolt has lifted weights as much as he can, has exercised as much as he can. He can't possibly exert any bigger force from his legs. He's maxed it out. But he wants to improve the acceleration. Which of those variables can he change? Yes! Lighter shoes, same force, slightly bigger acceleration. Now the mass probably isn't that big a difference because the shoes are pretty light already, but even if you could reduce it by a few grams, are those 100-meter races being decided in hundredths of a second and even thousandths of a second? Maybe that's enough to give you just a slight edge. As m decreases, a increases. So Newton's second law is the equation. As m decreases, a increases. Newton's third law. This is the most confusing or most misunderstood of the three laws. It's traditionally written, for every action there is an equal and opposite reaction. I've always found that ridiculously confusing. So here's Mr. Dewick's version of Newton's three laws. Forces come in pairs. Forces come in what? Pairs. Forces come in what? Forces come in pairs. You can't have a force by itself. You can't. You can't. It's going, really? You can't. Trust me. Forces come in pairs. I'll prove it to you in a second. Or if I want to write it mathematically, Abe, I would say this. If object A applies a force on B of magnitude F, object B applies a force on A of magnitude F, but in the opposite direction. How would I show? What would be a nice way to show in the opposite direction? No, negative, sure. Let's look at some examples. I need a volunteer. So how does Newton's third law help explain why it's difficult to walk or drive on ice? No friction means no force to accelerate. In fact, all of you, at least once in your life, especially on a wet field, may have experienced when you wanted to start really, really fast, when you wanted to go from a stop into a sprint, and you started to try to do so, and your foot slipped out because you were asking friction to give a bigger force than it could. And since it couldn't, your foot had to continue accelerating in the opposite direction because it couldn't match the force. We call that slipping. How does Newton's third law help to explain why professional boxers need to wear boxing gloves? Oh, you want a demo? Come on up here. Okay, I've had enough. I've snapped. I'm going to punch you square in the head. Here we come. Slow motion. So here's our high-speed camera. My fist is going to apply a force onto Kayvon's nose. Force is coming what? So what's his nose going to do? I'm going to apply a force back to my fist. Now his nose may break and I may do damage to him. Whatever damage I do to him, it's almost going to be back on my hand as well. Or what's the solution? What do boxers do? Boxing gloves. Which also, by the way, increases the mass, which is another way of increasing the force. In fact, believe it or not, you hit harder with boxing gloves than you do without boxing gloves. It's kind of counterintuitive. Everyone says, oh, look, they're soft. I assure you, you talk to any boxer, they would much rather get hit by a fist than by a boxing glove. Absolutely. Right? F of fist on face equals negative F of face on fist. Homework on this sheet here, called Newton's first and third laws. On the front page, you're just going to try and classify whether it's Newton first or third. How about a 1 for first? How about a 3 for third, whether it's an example of that? Some are examples of both, and I will take both answers. We'll go over the answers next class. On the back page, see if you can figure out what the pair force, what the reaction force is in those situations. And then see if you can articulate a good answer to number 2, 3, and 4. We'll talk about all of this next class.